Alright, I think that's going. My book. Looks like we just basically have 3 proofs to cover today. Yeah, that's it. So, should be able to get to it pretty quickly, I think. Hopefully, wonderful. Good marker. Alright, so first thing we'll prove is lemma 6.17. Let's see. You want me to have the book open?
Yeah.
Can you just read that to me?
Yeah, this one's.
F from A, B.
Okay.
Oops.
Okay.
So let the function f from AB to R be continuous.
And that P be a partition of its domain AB.
On AB.
And then there is a partition interval of P that contains 2 points, U and V, for which the following estimate holds.
Then there exists a partition interval, what?
Of P that contains 2 points, U and V. Okay, and then it's.
A lot of math notation. Probably easier to just this out. 2 points in V, U sub I, comma, V sub I. In that interval. Okay. Such that this all has one F of U sub I.
Hang on, I think you're going too far now.
Oh, whoa, yeah, I jumped way into the proof. Good thing you were paying attention. And there exists 2 points, U, V.
Such that 0 is less than or equal to.
The upper Darboux sum of F on P minus the lower Darboux sum of F with P, which can be less than or equal to F of V minus F of U? Yeah, must be minus A. Okay, and this actually makes perfect sense. So let's draw a picture really quick of what this is saying. So we've got some function. Here's A, here's B, some function defined on AB, right? And it does, who knows? And we've got some partition on it. So create some partition. Maybe do some dotted lines so we can see how everything lines up. And you know how to get your lower and upper Darboux sums, right?
Yes.
So your lower Darboux sum is all the rectangles when we stay under the line, but touching it at one of those endpoints. Or not necessarily at an endpoint, but just staying completely under the line. So there's our lower Darboux sums. And our upper Darboux sums, maybe since we've got some good markers we can switch out and not limit ourselves. Our upper Darboux sums look something like, Something like that, right? And so what this is ultimately saying is, there's going to be one of these partitions is going to have the max difference between the upper and lower W sum. So the V that they're talking about here is going to be the point on the function right here that corresponds to the highest point in the interval that gives us our biggest difference between our upper and lower W sum heights. And U is going to be the lowest point in that interval. U is going to be this point right here. So they're saying there's going to be one of these intervals is going to have the biggest difference between the height of your upper and lower W sums on that interval. So if we use just this difference for every single one of these, then we could have only made the difference bigger. So I'm guaranteed that now if I were to add up all these little rectangles here, their area would be less than if I just used this one and pretended every rectangle had a difference of this one's height.
Where in your proof did you say that U and V were those points?
Just what this right here is going to be saying, just what this inequality is going to lead to. We haven't proved anything yet. I'm just showing you a picture what we're going to be doing. So I'm going to find this for my V and this for my U. This is going to be my f of V minus f of U. Is this height, and then this height times the base gives me a big rectangle like this. So this is, that big rectangle right there is what this is going to be. And then this difference right here is adding up each of these rectangles independently. And since this was the biggest difference in height, I'm guaranteed this rectangle is bigger than the sums of all these little rectangles. That's what I'm proving. I'm proving that there exists some partition interval of P that contains points U and V such that this inequality holds. What's that interval going to be? It's going to be the interval that has the biggest differences in heights. That's what it's going to be. We're just proving that there is one. So pictorially, here's what we're doing. And then you can see how this might be useful down the road. I'm sure that we're going to use the fact, okay, now we can make this go to 0, which means that this is going to go to 0, and so the thing's integrable. The limit of this is going to, the limit of this difference is going to go to 0, so the limit of that's going to go to 0. I'm sure it's how this is going to come back to help us. But we'll see maybe now. Anyways, let us prove it. So, let P, we'll just assume that we already have F and P since we said let up there. Let's see. So, how do we want to say this? Because I already know the names of the smallest point on each of these intervals, we already had a name for that, little m sub I. So maybe a reminder about what this is. And for the highest point on each interval was big M sub I. So big M sub 1 is this point, little m sub 1 is this point. Big M sub 2 is this point, little m sub 2 is this point, etc. You remember that? And that's the notation that we had. So I think I'm going to want to use this to try and define how I get these points. So maybe I'll say let maybe we'll call it U sub I. Let U sub I maybe give them in a sec. Now I know what I want to do. I'm just trying to think of the right notation to use. Let's see, does he collect them in a set? Let P be that for each index I, since F is continuous. Oh, that's a good place to start. Okay, yeah. So let P, let's name P. P is going to be x0, x1, x2, dot, 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 all the way to xn. It's got endpoints in the partition. Since F is continuous, then f on the closed interval x sub I minus 1 to x sub I achieves, how do I want to say that? We want to say since f is continuous, then f on this interval has a minimum and a maximum by the extreme value theorem. So maybe say then by extreme value theorem, then by extreme value theorem. You remember the extreme value theorem? Almost says exactly what I just said. If you have a continuous function defined on a closed bounded interval, then the function obtains a maximum and a minimum on that interval. So we know that. So what we're going to do is look at this function restricted to just this interval and say it achieves a maximum in. On this interval, say it achieves a maximum in, etc. And we're going to call its max and its min little m sub I and big M sub I, respectively. Or other way, big M sub I and little m sub I.
Not just define them the way that they're defined.
I don't know that we can jump straight to that because that was just notation that we used internally in a proof. Or maybe he just feels like that, maybe it's been long enough since you've seen this that we better bring it back full circle.
Use some last section. Okay.
Yeah, but this is kind of like a just for our purposes type definition that we're using inside this room. Like, this isn't a definition for all of analysis when you pull this up. Oh, that's what that is.
So how do you define a Darboux sum in all analysis?
You define a Darboux sum where you also define these in the same go.
Yeah.
So then these are only relevant in the definition of a Darboux sum. This isn't a universally defined thing like a continuous function. It's a universally defined thing.
So I'm just wondering why we don't redefine it the same way, because it's exactly what we're saying.
It's basically what we're doing right now, is redefining it the same way.
Okay.
So, since f is continuous, then by the extreme value theorem, f has max and min value on x of I minus 1 to x of I, comma, call them big M sub I and little m sub I respectively. Respectively. 3. Okay, so now what do I want to do? I want to find the max difference between big M sub I and little m sub I. So I'm going to look at the difference between big M sub I and little m sub I here, 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 and here, and I want the maximum. So let, and we need a name for the interval, so maybe I'll say let,
Isn't it x naught?
in this special case, it was x naught to x1, but this was just some random function. It could have been over here. So we need this is a particular case, we need a general way of saying it. What's his notation for using that? Okay. So let I sub 0, little I sub 0, be the index such that big M sub I sub 0 minus little m sub I sub 0 is equal to the max of m sub I minus little m sub I for 1 less than or equal to I less than or equal to n. That's the notation is using to find the max. So go over all n of our intervals, right? Partition, notice n is defined by our partition. Our partition has n intervals in it. So we have n intervals. This is saying take the max of all those differences, and they're going to have an associated index right there. Right? So in our case, it was 1. It was the first one. So this I naught is 1. He's just using I naught. Maybe we should just say j rather than I naught. Let j be the index such that n sub j minus. So now I is an iterating index that goes over, and j is a particular index. It's one and only one index. In this picture over here, it's 1. Okay, is that clear now? So then, that's our define. We're going to have u equal to m sub j and v equal to big M sub j. So there's our u and our v now. And now we just need to show that this inequality holds, which obviously it does, but we'll write out the algebra to see it. So 5. Then 0 is less than or equal to our upper Darboux sum from I equals 1 to n of big M sub I times x sub I minus x sub I minus 1. Go with that for our upper Darboux sum still. Don't need to re-go over that. Minus our lower Darboux sum. The sum from I equals 1 to n of little m sub I times, that's an I, times x sub I minus x sub I minus 1. Okay, now notice that I have a difference of two things where I keep multiplying by the same values over and over and over again. So in other words, I can basically factor out an m sub I minus an m sub I minus 1 from both those, since they're summing to the exact same terms. Does that make sense? Let's do a picture of it real quick. If I have 2 times a plus, let's see, what's the easiest way to see this? Because those numbers are going to change. But they're going to be the same number. Maybe keep these the same for a second to help us see it. So just pick some random heights. 3 times a plus 2 times a plus 2 times a. Let's pretend that that's something like what this sum looks like. And now we're going to minus from that. And we'll just say 2 times a plus 1 times a plus 1 times a. So we have a sum of some products like this, and we have minus a sum of some products like this. What can I do? Since they're always using the same A, those A's could have varied. It could have been A, B, and C. Maybe that will be better to see it that way. A, B, and C using the same values, B, C, C. Because these are always going to be the same for a particular I, right? So when I is 1, we'll call it A. When I is 2, we'll call it B. When I is 3, we'll call it C. So still see how it's similar. Now, when we have a difference like this, we can get all our A's together. That would have been 3 minus 2A, and then we would have plus 2 minus 1B plus 2 minus 1C, like that, right? And we didn't change anything. Still good? So now we're still doing that difference of these two terms times A plus the difference between those two terms times B plus the difference between those two terms times C. That's the exact algebra I'm going to do right here. So I'm going to rewrite this as the sum from I equals 1 to n of big M sub I minus little m sub I times, I don't know why I use square brackets there. Probably should use round brackets so we don't accidentally think it's an interval. X of I minus X of I minus 1. You okay with that algebra? Okay. Now, just use what we know. I know that by definition, U and V, oh, u and v are supposed to be the points in the domain. Oops. So I want f of u to equal that and f of v to equal that. Because u and v are supposed to be in the domain, and these are the heights at those points. So sorry about that. So let me clear that up. Define u, v such that f of u is equal to little m sub j, and f of v is equal to big M sub j. So over here, u is actually this point, f of u is right there. V is actually this point, f of v is right there. That makes sense? Sorry about that. Okay. So then we have that is equal to that is equal to that. Now this, by definition, if I replace this with big M sub j minus little m sub j, we only make the value bigger, right? Which is the same thing as f of v minus f of u. So this is less than or equal to the sum from I equals 1 to n of f of v, maybe we'll do square brackets there, sum of f of v minus f of u times x of I minus x of I minus 1. Okay with that? Now notice now this value, whatever it is, whatever that difference is, doesn't change with I. That's now just a constant for this whole sum. So when you plug in I equal to 1, you get a number here. When you plug in I equal to 2, you still get the same number. When you plug in I equal to 3, you still get the same number. So we can factor that out of the sum. It's in no way dependent on I. So now, this is equal to f of v minus f of u, sorry I did the round ones again, oh well, times the sum from I equals 1 to n of x of I minus x of I minus 1. But what is the sum of all these intervals?
It's b minus b.
Other way,
You
B
like
minus.
b minus a, right? It's this total difference.
Yeah.
If I add up that difference, that difference, that difference, that difference, that difference, that difference, I get this difference. So, and that's going to finish our proof. So this is equal to, use square brackets this time, f of v minus f of u times b minus a, which is what we were after. Any questions there? Anything weird? We're good? Oh, looked like you were getting ready to ask something. Okay, so that was the lemma. Theorem, a continuous function on closed bounded interval is integrable. Okay, so this is the one we've been waiting for. So let's prove that. Which means I'm going to use, we know that function on a closed bounded interval are uniformly continuous, which looks like, yeah, he's going to use that fact. Okay, so quick recap on uniform continuity. It's a stronger notion than continuity. What uniformly continuous functions were continuous functions such that you can bound how much they grow on a certain interval. So let me give you an example of a function that's not uniformly continuous as a counterexample. And then we'll re-intuitively go over why any bounded continuous function, any continuous function defined on a closed bound interval is always uniformly continuous. But so here's an example of a function that's not continuous. F of x equal x squared. Sorry, not uniformly continuous. It's continuous, but it's not uniformly continuous. Why is this function not uniformly continuous? I pick as an interval on the domain a length of 1. So now we're looking at intervals of length 1 on the domain of this function. What does this function look like roughly? It looks something like that, right? So I pick a length of 1, and I can stick this anywhere on the domain I want. Your job is to find a number such that no matter where I stick this on the domain, my function doesn't grow by more than the number you choose. And it doesn't matter how big of a number you pick. You might pick 10,000. So is it possible for me to find somewhere in the domain such that this function grows by more than 10,000 in that one unit? And yeah, the further I go to the right, the more it grows, and I can go as far to the right as I want and make it grow as much as I want. So this function is always bounded. Or so this function is never, its growth on a particular interval is never bounded. That wasn't the definition, that's just how I keep it in my head to remember what this means. We'll go over the exact definition of uniformly continuous again, but this is the intuition for what it gives you. And how the definition connects to the intuition isn't obvious, so I just kind of remember both of them, that here's the intuition and here's the definition, and how those two things connect. It doesn't appeal to my intuition, so just warning. But intuitively, that's what it gives us. So now we have a function defined on a closed bounded interval from A to B, and it's continuous. Doesn't matter where I start, and it doesn't matter where I end, how much I grow in that time. Well, we can't have it do that, because now it's not a function. Oops. But I can try and make this thing do any crazy thing I want, but it achieves a minimum value and a max value by the extreme value theorem. And so the function, doesn't matter what interval you grow by, can't grow by more than the max minus the min. So you can always bound how much you can grow on a particular interval because it's bounded by its growth overall. Does that make sense? So that's the intuition for why continuous functions on a closed bounded interval are uniformly continuous, and it's also something that we proved. But that's the intuition for it. So now what does uniformly continuous give us? It gives us that.
So, remind me, did we prove that a function on a closed bounded interval is uniformly continuous? Oh,
Yes, we did prove it. So it tells us that the limit, that if the limit of un minus bn is equal to 0, that implies that the limit of f of un minus f of en is equal to 0. You remember continuity in general, right? Continuity was if the limit of xn is equal to 0, that implies that the limit of f of xn is equal to 0. That was our definition for a continuous function. Why are you seeing now? What's throwing you off?
I feel like something's off.
Oh, sorry. If this is equal to x naught, then this is equal to f of x naught.
Yeah, that makes more sense.
I should have written it as a difference. If xn minus x naught is equal to 0,
Yeah.
then this is the way to see how they're related. Okay. There we go. Yeah, I had a root before. Okay. So here we just got a constant, here we got a constant. If you can do it with two sequences, then it's uniformly continuous. And that's the relation between continuity and uniformly continuous, and you can see why it's kind of has its name. Okay, so we're going to be using this fact in here. Not sure how yet, but the fact that we've got using these just always brings uniform continuity to mind, so let's figure out how to do the proof.
Aren't those two things saying basically the, oh, no, right, okay, that makes sense.
Yeah, remember that here we've got two sequences, here we've only got one sequence.
Right.
Yep, that's the only difference. Okay, so, maybe I'll also leave this up here because we're obviously going to be using it somehow. So just to remind myself, obviously, since it's a lemma. And our theorem is going to be just next here. I want me to see. Theorem 6.18. And we're proving that the continuous function on a closed bounded interval is integrable.
functions on closed bounded interval continuous? No, what did we prove? We proved something similar. Yeah, that's right.
I guess, you know, leave it open to learn, etc.
Yeah.
Weird.
Isn't it supposed to be uniformly continuous?
If f is continuous, then f is integrable. A continuous function on a closed bounded interval is integrable. Now, but I'm assuming that, let's see, to prove this we will use Archimedes-Riemann theorem. And so he just references it somewhere in the middle. He just says, but a continuous function on a closed bounded interval is uniformly continuous. So we just have that as a fact that we know that we can rely upon. So since it's on a closed bounded interval and since it's continuous, as we go through this proof, we're going to use the fact that it's uniformly continuous. So let's see what we can do, and then if we get stuck, we'll further explore. Okay. So I'm trying to show that a function is integrable. How do we show that? I need to show that the limit of its upper and lower Darboux sums go to 0. Right? So I need to show that the limit of this goes to 0. Since I'm going to be using this as a lemma, obviously we're trying to set up a situation where this goes to 0. So that's ultimately what we're going to try and do. So, and we know that we can let Pn be an, well, we can't just call it an Archimedes-Riemann partition because then that implies that it automatically works. But we want it to be a sequence of partitions such that the gap goes to 0. Let Pn be a sequence of partitions such that in the limit the gap goes to 0. Yeah, that's good. Okay, so that's good. In the limit, we can put as n goes to infinity here. Did we define gap as an operation? So I guess we did. Gap of Pn is equal to 0. So Pn, sequence of partitions, as n goes to infinity, all we know is that we picked some partition, some sequence of partitions where the gap goes to 0.
That means it's an Archimedean sequence?
No, we're going to prove that it is. An Archimedes-Riemann sequence, or whatever we call them, is going to be one where this happens such that this difference goes to 0. Because if such a sequence exists, then we know that the function is integrable.
We're going to set it up like that and then prove that it is.
Yeah, we can always pick one that makes the gap go to 0. We can just keep dividing the intervals up into even pieces if we want. There's one. So, but we need to show that for anyone that satisfies this, then this is going to work.
The gap of Pn is the largest interval of that partition?
Mm-hmm.
Okay.
Yep, so we just have to require that our largest interval keeps getting smaller and smaller as time goes on. Okay, so 2. Let's see. Let the function now be continuous and let P be any partition. Okay, so for a given partition, maybe we'll call it P sub I, comma, define U sub I and V sub I such that this holds, such that 0 is less than or equal to the upper Darboux sum of f when we plug in that P sub I, minus the lower Darby sum of f when we plug in that p sub I, which is less than or equal to f of v sub I minus f of u sub I times b minus a. For a given partition pi, define ui, vi such that this is true, comma, and let un, vn be their sequences or something like that. Kind of a bad way to say this, but I think you get what I'm saying. Let un and vn be the sequences of those u sub i's and v sub i's. So for any particular partition you choose, so we take p sub 1 here, this holds for that partition, right? This holds for any partition on a function like this. Does that make sense? Three. Now remember that u sub I and v sub I are always picked from the same interval. We found the interval, we erased the picture, we found the interval that had the biggest difference between them. The max and its min. And our u sub I was the point in the domain that went to the min, and our v sub I was the point that went to the max. So up here, we're saying, look at what this says again, let's just go over it one time. Let the function f from ab to r be continuous, and let p be any partition on the domain of the function. Then there exists a partition interval containing both these points such that this is true. So u sub I and v sub I are always in the same partition interval. They might be in a different partition interval than u sub I plus 1 and v sub I plus 1. I'm not saying we're using the same partition interval for every partition. I'm saying pick a partition, then u and v are in the same partition interval. Does that make sense? And we know that the gap of our partitions as n goes to infinity goes to 0. And since u and v are always going to be in the same interval, they're forced to get closer and closer and closer together, whatever interval they're in. Does that make sense? Here's where I'm going to put that all together. Since u sub I, maybe we can use u sub n here. Since u sub n, v sub n are always in the same, no, we'll use u sub I and v sub I here and use the n's to reference the sequence rather than a particular one. Since for a particular u sub I and v sub I, they're always in the same partition interval, and since the limit, we won't do as n goes to infinity, that's obvious now, the limit of the gap of p sub n is equal to 0, then the limit of the difference, doesn't matter which one we do first, but we'll do v first since we usually think about it. Well, it's in the domain, so it doesn't matter about the difference between those, in the sequence now, is 0. So since the biggest partition interval's length goes to 0, and since these two are always in the exact same partition interval, the distance between them has to go to 0. Does that make sense? And now we're using the fact that we know that f is uniformly continuous. Since f is uniformly continuous, then we know that the limit, as n goes to infinity, of f of v sub n minus f of u sub n is equal to 0. That's from the definition of uniformly continuous. Okay, now just put this back together with that inequality, and we're done. So 5. Then 0 is less than or equal to the limit of the upper Darby sum on f of Pn minus the lower Darby sum of f on Pn, which is less than or equal to the limit of, gotta do two things here, so I'll use curly braces, of f of Vn minus f of Un times B minus A, which is equal to, we know that this goes to 0, times B minus A is equal to 0. Gives me that f is integrable. Because the limit of its difference between its upper and lower Darby sum is 0. That was the Archimedes-Riemann theorem. Any questions on that one? Anything weird?
Are you, I understand why the upper minus the lower Darby sum goes to 0, but are you using the comparison lemma to do that, or is there like another theorem you're referencing here? Or is it just logic?
You're saying the fact that since this is less than or equal to this, the limit of this is less than or equal to the limit of this?
I'm saying that because 0 is less than or equal to something is less than or equal to 0. Well, yeah, okay. It's pretty obvious. Okay.
Oh yeah, so
I was wondering if there was a theorem or if it was just logic. If it was just logically followed.
so we end up with this difference is sandwiched between 0 and 0,
Yeah.
which makes it 0.
Yeah.
Yep. Anything else? Okay, let's start the next one. Next one looks like it's a bit of a mouthful. This one's easy enough to memorize. I'm going to keep the lemma up there in case we need to reference it again, because that one's not as easy to just say. But we know the results of this theorem. A function defined on a closed bounded interval is a continuous function defined on a closed bounded interval is integrable. But if we need to reference that one again, it's not as easy to just say. So let's see. Theorem 6.17. Not 6.17, 6.19. Not sure why I said 7. Okay. Suppose the function f from ab to r is bounded on a closed interval ab and is continuous on the open interval ab. Let f from ab to r such that f is bounded and f is continuous on the open interval AB. So it's bounded over all, and we only know that it's continuous on this internal interval, might not be continuous at the two endpoints. Then f is integrable on AB, and the value of the integral does not depend on the values of f at the endpoints of the interval. Okay, that's kind of a weird one. Excuse me. Then f from, well, we already said what it's from. Then f is integrable and the value of the integral from AB to f does not depend on the endpoints. Okay. Let's make intuitive sense of what this is saying. because intuitively, it seems pretty clear. So I have a, b, I've got some function defined on a, b. Something like that. But it could have a hole there, and it could have a hole there, and maybe the point here is down there, and maybe the point here is up there. What's up?
We're just checking on the classroom, make sure it's full.
Alright, feel free.
Check the same.
Alright, so now, if we look at the area under the curve, when we remove those points, removing those points shouldn't change that area, right?
We did a problem almost exactly like this for
Probably, maybe he'll say somewhere in here, from exercise blah blah blah. This author sure likes to do that. Almost every math author likes to do that. So lazy. If you're going to require something to be covered for later theorems, just cover it. Come up with other problems. I hate it when they do that. Okay. Let's see. So let f from a b to r such that f is bounded. Okay. 1. Since f is bounded, then there exists m in r such that negative m is less than or equal to f of x is less than or equal to m. Right? If it's bounded, then we can sandwich the scene from above and below by some big number m.
So m is like the max.
It doesn't have to be. We can go way past that. We don't need to try and find some really close m. We just some big number. So f is bounded, and then f is continuous on the open interval AB. So maybe we'll take a partition, some like small partition that's only on here, and then re-add in the end pieces. Sorry, kind of just thinking out loud. I'm thinking that we'll do something like, here's A, here's B. I think we'll create some partition inside of A and B, whatever it is. And who knows what our function does. Just draw something up here that could potentially be it. Our function could look something like that. That's like worst case scenario, right? So what I'm thinking is if we define our partition starting here and ending here, so we kind of like remove our endpoints from it, then we know that the function behaves nicely on this partition, because then it's always closed bounded intervals, like from our previous theorem. So I can integrate all those individual things, but then we're back to the problem of trying to integrate that.
Did you?
If I take a sequence that gets closer and closer to A and closer and closer to B, we eat up that difference. A sequence of partitions, so I think 2, we can just use A n at the end. Let A n be n such that, and I want an, these are going to be the endpoints where I do my partition. So I want an always to be to the left of bn, and I always want it to be greater than a less than b. Okay, so we want a less than an less than, we won't do equal to, otherwise we won't do anything. Bn less than b, where the limit of an is equal to a, and the limit of bn I've got a_n and bn are two numbers that are always going to be inside of here. So our function is going to behave nicely from a_n to b_n. And I've also got them such that they keep getting closer and closer to a and b. So we're like stretching out our interval that this function is going to behave nicely on. Make sense so far? I'm not sure where I'm going with it, but. And then we're going to want to define a partition from a and to bn. But we're also going to need a partition that includes a and b, so we'll use a prime for this one. Let Pn prime be a partition such that the gap goes to 0. Could I even just say, well, we'll leave it here for now, such that, alright, let's let me go through this. I don't want to go down a bad rabbit hole. Come on, wake up. My laptop died? I don't know. Maybe okay, it's bounded, yet choose a_n and bn such that, okay, we did that exact thing, that's good. Fix an index n, then f from a and to bn on R is continuous, and by the preceding theorem, f is integrable on a and bn. It is therefore a consequence of the Archimedean-Riemann theorem, so that there is a partition p star n on a n. Okay, that's a good way to do it. So we're fine with everything we said here. It's in getting this partition to make it do what I want that I was getting a little stuck on. So what the author's saying is that we know that, maybe just write it out, since f defined on the restricted domain, a and bn, is integrable, then there exists some sequence p prime n, or he used a star, I guess, follow his notation. There is some partition p star n that is an Archimedean-Riemann sequence of partitions. So then there exists p star n such that the limit of the upper Darboux sum of f using the sequence minus the lower Darboux sum of f using the sequence is equal to 0. But if it converges to 0, he also says is less than, we do just less than 1 over n, but we might do less than or equal to 1 over n. We can make it as small as we want. Oh, not in the limit. Okay, now I'm going to have to think about this again. What do you think? So he's saying such that 0 is less than or equal to the upper Darboux sum of f with p star n minus the lower Darboux sum of f with p star n, which is less than 1 over n. Let's see. Just because I know that that sequence read what he says. By the preceding theorem, f is integrable on the closed interval a into bn. It is therefore a consequence of the Archimedean-Riemann theorem that there is a partition p star n of a and bn such that that inequality holds. Using exercise 4. Oh, lovely. So let's try to make intuitive sense of this real quick, we can always find, because it is integrable, we can always find a partition that makes the difference. That doesn't make sense. Okay, so since I know that the difference of these converges to 0, I know that for any small number you choose, I can find a partition that makes this less than that small number you chose. Going back to think about the way we thought about limits. Okay, so that's how that one's ultimately going to be justified. I assume, I don't know if I gave you exercise 4. But
What does exercise 4 say?
well, he makes it sound like it says that basically if the difference of this limit converges to 0, if you have a sequence of partitions such that in the limit this difference converges to 0, prove that there exists a particular partition satisfying this for any n that you choose.
So P star n is a sequence of partitions, right?
It's a particular partition in the sequence of it. We're referencing a particular one. We could have said I, such that 1 over I if we want. It's just we're going to use this in a sequence now to show that it's going to go to 0.
Okay.
You sure you got it? Right now, this is a particular one. Then there exists some sequence of partitions. Notice that we're going to do this for every a_n and b_n. So pick an n1. Okay, so now we have a1 and b1. Then there exists p star 1, such that this is true, and it's less than 1 over 1. Does that make sense? And then you can do it for 2, 3. So that's why we're using an n here. So we're coming up with a way to talk about the sequence of partitions. But here this is referencing a particular partition, just showing you how to do it in the nth case. Does that make sense now? Alright. Define Pn. Okay, yeah. So now we need to throw in our endpoints. Define Pn to equal P star n union with the points A, B. So putting those points back in there, so now Pn is on the whole thing. So P star n might have started here and ended here. Pn is saying now throw in the endpoints real quick.
Why?
Notice, ultimately what we're going to be doing is showing that the value of this does not depend on the endpoints, right? So I'm going to be showing that the rectangle that you get here at this end and the rectangle that you get here at this end ultimately go to 0 in these limits, since as a n approaches a and b n approaches b.
Are these the same a and b that you have on your picture?
The a and the b are the same. A_n is a sequence of the left-hand points that we're using. So here's my a_n in the picture I've drawn. Here's my b_n in the picture that I've drawn.
Oh.
And they're going to keep getting closer and closer and closer. So our partition is going to include more and more of our interval.
Right, sorry.
And it gets arbitrarily close to a, never quite approaching a. The contribution from the first rectangle and the last rectangle are going to get closer and closer to 0. In the limit, they're not going to make any contribution, showing that the value of the integral doesn't depend on the start and end rectangles, showing that it doesn't depend on the start and end points, the values of those points. That's where we're going with this, I assume. That's the way it makes sense to me. We're slamming a lot. Command 4, define Pn equal to P star n union with the points A, B. Okay, so now I think we're ready to start comparing actual values of sums. Maybe he's got a picture there, that's a good idea. So the value of these rectangles here, we're going to give them an upper bound. the value of this rectangle here is for sure going to be less than or equal to 2m times a sub n minus a, where a sub n is the nth term there. This is the width of the rectangle, right? This is the width of that rectangle. You with me on that? And now the height of this thing, we know that this thing's bounded, so m is somewhere up here, and negative m is somewhere down here. In this case, this function happened to be always positive, but it could have jumped who knows how. But the point is, this height couldn't have been more than 2m, since it's bounded, the height of the rectangle. Since I know that the whole function is between m and negative m, the distance from here to here is 2m. Therefore, whatever this rectangle does, there's no way it has a height more than 2m. So it's going to be bounded by this value. Similarly, over here, we're going to have it bounded by that value as well. Does that make sense? He's got a nice picture of it in the book, but he's going to call the area contributed by this thing, this one's area, we're going to call big A sub n, and this one's area we're going to call big B sub n. So once you pick a particular n, the area for the first rectangle we're going to call big A sub that n, and the last rectangle we're going to call its area big B sub that n. And we're going to be showing that those things go to 0. So, I think he's ready to just define those. Define Pn. Yeah, okay. 5. Observe that the upper Darboux sum of f with Pn now minus the lower Darboux sum is less than or equal to the upper Darboux sum of f with Pn minus the lower Darboux sum of Pn star, minus the lower Darboux sum of f Pn star, whatever the difference of areas were on those two, plus An plus Bn where A and Bn are the two areas I said. You still with me so far?
If Pn is a partition, what does it look like to have a union with just the set A and B?
Oh, remember that it's just, a partition is just a set of points.
Oh, that's right, it's not equals. Sorry.
Sorry. Yeah, the author doesn't use notation like that. He kind of, I like to keep it clear to the mind. We're just talking about sets of points.
Yeah.
So anytime I add partitions, I like to just put unions in there to keep that clear. Any other questions so far? So continue with this inequality then. So now this is less than or equal to exactly what I said here. It's going to be less than or equal to that value. So this is less than or equal to, still we have the upper Darboux sum of f with P star n minus the lower Darboux sum of f with P star n plus, instead of that, we're going to write this, 2m, notice we already defined m somewhere up there, our first line, 2m times an minus a. I know that an is always greater than a by definition up here, so that difference is always a positive number, plus 2m times b minus bn. Any confusion in any of that? Okay, now we just take the limit. Then, the limit, as n goes to infinity, of u f p n minus l f p n going to be less than or equal to the limit as n goes to infinity of UF P star n minus LF P star n plus 2m, kind of ignoring this middle step and going straight to this one. 2m an minus a plus 2m bn minus b, which is equal to. Now, the limit of the sum is the sum of the limits, right? So I can pull these two outside the limit and take their limits separately
They're
and
both
leave
going,
these ones together.
they're gonna go to 0, right?
Exactly. Infinity of the upper of f with p star n minus the lower of f with p star goes up, p star n, that's p. And then pulling these two out and taking their limits just gives me plus 0 plus 0. You okay with that? Okay. I kind of need to argue that, therefore, the limit of this difference, let's see. How do I want to say that? Here, let me kind of talk out loud, and then maybe that will help me see how to do it. Because I'm trying to show two different things here. I'm trying to show, first off, this is integrable, right? So let f from ab to r such that f is bounded and f is continuous on the open interval. Then f is integrable. I'm trying to show that. And I'm also trying to show that the value doesn't depend on the endpoints. So notice that when we're looking over here, the value doesn't depend on the endpoints. Here, the value does depend on the endpoints. So I need to show that basically the limit of one of these is equal to the limit of one of these, but I also need to show separately that the limit of this difference goes to 0 first. So showing that the limit of this difference is 0 tells me that it's integrable. And then I need to come back and say, and also the limit of this thing is equal to the limit of this thing. Picking one of them, doesn't matter which one. So I was trying to show that the limits are equal before showing that it's actually integrable, which I probably shouldn't have done. I should have gone straight to showing that everything's 0. So maybe I'll just write right here and then we can reference this equation twice. Which is going to be equal to, we already know that this difference is going to be 0. Because the function is already integrable on the interior parts. And these are partitions on the interior. These are always on this, and we know that the function is integrable on that already. So I know that this is also evaluated to 0. The whole thing is evaluated to 0. The reason I just evaluated these parts first was because I was going to try and argue that this is also the same as this. So I was getting ahead of myself. Should have gone straight to just saying it's 0, but we'll go back to that. So first let's understand that this whole thing is 0. Is there anything weird there? Make sense that it's 0 and why it's 0? Okay, so since it's 0, then that gives us that f is integrable, which gives me that the integral from a to b of f is equal to the limit as n goes to infinity of, doesn't matter which one we pick, we can use upper or lower, of fpn, right?
How did you conclude that as integrable?
Because this limit is 0.
Because it's also greater than or equal to 0?
Oh, yes, sorry. yeah, our upper Darboux sum is always a bigger value than our lower. So yeah, I should have started with 0 is less than or equal to blah, 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 blah. Sorry about that. That's absolutely right.
If you did, you'd know they're equal, wouldn't you?
I know what are equal?
That your two limits are equal, and that's what you're trying to prove. Now that you know that.
Yes, yes I do. But you'll see why I had to come back to this symbol first. Because I'm saying that they both give me the integral. So, you've got the right idea. You're seeing everything that I'm right about to use. So, we know that the limit of the difference between the upper and lower Darboux sum goes to 0. Therefore, it's integrable. F is integrable, right? Therefore, the integral of it is equal to the limit of the upper Darboux sums. We could have also used the limit of the lower Darboux sums. Doesn't matter. Right? You remember calculating integrals by hand. I don't know which one you use, lower or upper, but you use one of them, typically, and you could have used something in between if you wanted. But now, from exactly what she's saying with the inequality, or from this line up here, we also know that this is the same thing as the limit, as n goes to infinity, of the upper Darboux sum of f with p star n. So now we see that the integral doesn't depend on the endpoints, the value of the integral. See how that all ties together now?
How does that tell you that the value doesn't depend on the endpoints?
Because p star n doesn't use the endpoints.
Oh. Yeah.
So p star n is giving us the area from an to bn and stopping. Anything else? Let's see if we miss some subtle detail that he points out. Thus 0, however, by choice of sequence an and bn, all those limits go to 0. Therefore, the limit of the upper, thus Pn is an Archimedean sequence of partitions. Thus, the integral is equal to the limit of the upper Darboux sums, the one he chose. But the difference between the upper with Pn and the upper with P is going to be 0. Which is exactly what we said. I mean, we could have specified one more, so he took the time to write in the step. Notice this limit, the limit as the upper Darboux sum of f with Pn minus the upper Darboux sum of f with Pn star is equal to 0. And so then he concludes this.
How did he get that?
How do we know this is true?
Yeah.
What is their difference? Their difference is just going to be, in this case, it's going to be bounded by adding these two numbers, which is going to be 0. We can write this out if it's not as obvious as I thought it was.
No, it's obvious. Well, it seems intuitively obvious. I just don't know, like, how do you...
We can prove it. So we can prove that the upper of f, Pn, minus the upper of f, P star n, is, first off, let's see, make sure this one is bigger than this one always and forever, right? Because this one includes an and bn, this one doesn't. So 0 less than or equal to upper minus that. With me so far? And then this is going to be that same less than or equal to, same difference. Oh no, it's just less than or equal to. Let's write what exactly this is equal to, and then I think the less than or equal to will become way more obvious. If I take this one and I minus this one, then all I'm left with is an plus bn. All I'm left with are the two end areas. And now we know that this is less than or equal to 2m times an minus a plus 2m times bn minus b. And take the limit, and you get 0. So that's the algebra for it. Anything else, Bird? Okay, that was it for today. So, go on break, and then you have the rest of class to start preparing for the massive final.